Section 6.1, exponential functions. An exponential function is any function that can be written in the form of f of x equals a times b to the x. B, which is the base of our exponential function, is always positive but can never be 1. A itself will also never be 0. If a was 0, anything times 0 is 0. So in that case, f of x would be linear and not exponential. Exponential functions are used quite often in modeling what we call exponential growth and decay problems. When a is positive and b is greater than 1, then f of x models something that we call exponential growth. Exponential growth refers to an increase based on a constant multiplicative rate of change over equal increments of time. That is to say, a percent increase of the original amount over time. In exponential growth, instead of adding some sort of value to our dependent variable each time our independent variable increases by a fixed amount, here we're multiplying by some value bigger than 1. On the other hand, when a is positive but b is between 0 and 1, then f of x models what we're going to call exponential decay. Exponential decay refers to a decrease based on a constant multiplicative rate of change over equal increments of time that is a percent decrease of the original amount over time. So exponential growth and decay both refer to us multiplying our dependent variable by some fixed factor as our independent variable changes by a fixed amount. This differs from linear models, where linear models involve us adding a fixed amount to our dependent variables. Keep in mind what determines exponential growth or decay is the size of b. If b is bigger than 1, then we have a growth. We're multiplying by a value bigger than 1, which causes our dependent variables to increase. On the other hand, if we multiply our dependent variable by a value between 0 and 1, that's going to cause a decay, since our dependent variables will get smaller when we multiply by a number between 0 and 1. Now we're going to take a look at the graph of exponential functions. To help us understand the graph of exponential functions, we'll start by looking at the graph of f of x equals b to the x. The reason why we can ignore a in trying to understand the graph is all a would do is cause a vertical stretch or shrink, or if a is negative, also cause a reflection over the x-axis. There's two possible graphs for f of x equals b to the x, and the shape of the graph depends on the size of b. If b is greater than 1, then f of x is an increasing function, as we can see with the orange graph on the right. We can also see in the orange graph on the right that the graph will get closer and closer to the x-axis on the left-hand side, but never actually cross the x-axis. The reason why our graph of the exponential function will never cross the x-axis has to do with how we evaluate negative exponents. Recall that when we try to evaluate b to a negative power, in this case b to the negative x, that equals 1 over b to the x. Well, if x is positive, b to the x we know is positive, so 1 over b to the x would also be positive. So no matter what power we raise b to, whether it be positive, negative, or 0, we're going to get a positive value out of it. So our exponential function will never cross the x-axis because it can never be 0 or negative. If our b is between 0 and 1, then f of x would be a decreasing function, as we see in the graph in green, and it's going to be getting closer and closer to the x-axis, but this time as we trace to the right. Now, I do just want to reiterate that the exponential function f of x equals b to the x will never cross the x-axis. Now, because we know that the exponential function will never cross the x-axis, the range will be 0 to infinity. Now, the domain is going to be the set of all real numbers. We can take any value of b that is positive but not 1, raise it to any power we want, we will get an answer out of it. So just like with quadratic functions, the domain will be the set of all real numbers. Next, we're going to write an equation of an exponential function that passes through the point 110 and 580. Does this equation represent an exponential growth or exponential decay? First, we're going to write our equation. Our equation, from what we've seen in past slides, would be y equals a b to the x. And we're using y instead of the function notation just to make the writing a little easier. One point we know our exponential function passes through is the point 110. This tells me if we plug 1 in for x, we should get 10. So we have 10 equals a times b to the first, but b to the first power is just b. So from the point 110, we know that 10 equals a times b. Unfortunately, I don't have enough information yet to figure out the value of a or b. So let's take a look at the second point we're told. Our exponential function can also pass through the point 580. This means if I replace x with 5, I get 80 for y. Here I have two equations with a and b. Now, we've seen in past sections solving systems of equations how we could add and subtract equations to try to eliminate a variable. But we're not just limited to adding and subtracting. We could also multiply or divide equations. Since I see a is a common factor of the right-hand side, I can eliminate the a if I divide my two equations. So if I take the second equation, 80 equals ab to the fifth, and divide by the first equation, 10 equals a times b, we can see in the result of the division, the a's would cancel. And when I simplify b to the fifth over b, I get 8 equals b to the fourth. Then to finish solving, we would take the fourth root of both sides. Now, because 4 is an even root, technically we do need the plus or minus. However, recall from the earlier slides, the base of our exponential function is always positive. So b would actually be positive fourth root of 8. Now that I know the value of b, I can use either one of the two equations to figure out a. Since the power of b is smaller in the first equation, I'll go ahead and plug in the first equation. So we have 10 equals a times the fourth root of 8. Divide both sides by the fourth root of 8, and we get 10 over the fourth root of 8 equals a. We can rationalize by multiplying the numerator and denominator by the fourth root of 2. The reason why I'm picking the fourth root of 2 here is 8 times 2 is 16. And we can take the fourth root of 16, which is 2. And if we simplify a little bit more, the 10 and the 2 reduce, and we get that a equals 5 times the fourth root of 2. So what is the equation of our exponential function? That would be y equals 5 times the fourth root of 2 for a times the fourth root of 8 raised to the x power. Since they did say function, instead of putting y, we'll replace it with f of x for the function notation. Now that we have our equation, let's determine if this represents an exponential growth or an exponential decay. If we take a look at our base, which is the fourth root of 8, the fourth root of 8 is bigger than 1, which you can check in a calculator. Since the fourth root of 8 is bigger than 1, then our function would represent an exponential growth. Next, we're going to write an equation for the exponential function that passes through the points -2, 18, and 3, 2 over 27. And then we're going to determine if it represents an exponential growth or decay. Just like in the previous problem, we're going to take each point and plug them into what we know the form of our exponential function to be. So the fact that -2, 18 is on the graph of my exponential function, this tells me 18 equals a times b to the -2nd. For now, we'll keep the negative exponent, so that way it makes it easier to divide later. The point 3, 2 over 27 tells us that 2 over 27 equals a times b cubed. Now notice that we see a as a common factor in both equations, so we'll go ahead and divide the equations. To make the solving of our resulting equation easier, we'll put the a times b cubed in the numerator of our division, and the a times b to the -2nd in the denominator. Notice on the right-hand side that the a's cancel. B cubed divided by b to the -2nd, when we subtract the exponents, give us b to the 5th. As for the 2 over 27 divided by 18, we'll treat the 18 as if it's over 1, and when we divide by fractions, we multiply with the reciprocal of the second fraction. So now we need to do 2 over 27 times 1 over 18, a little bit of reducing before we multiply, and we get 1 over 243 equals b to the 5th. Take the 5th root of both sides, and we get b equals 1/3. Now that we know b, we can plug it into either of the two equations and solve for a. Even though the first equation has the negative exponent, because our b is 1/3, I'm going to use the first equation since the negative exponent is going to flip the 1/3. So plugging b equals 1/3 into the first equation, we have 18 equals a times 1/3 to the -2nd. 1/3 to the -2nd is 9. So we have 18 equals 9 times a, which means a equals 2. So what is the equation of our exponential function? Y equals 2 times 1/3 to the f. And to use the function notation, instead of saying y, we'll put f of x. Lastly, is this a growth or decay? Because our base 1/3 is between 0 and 1, this tells me this function will represent an exponential decay. In this problem, a population of 100 turtles is increased by 20% every year. We're going to start off by writing a formula for the population of turtles after 2 years. First, we need to determine what kind of model is appropriate here, linear, quadratic, or exponential. To do this, we have to think about how we would calculate the number of turtles year after year. The key in determining how we would calculate our turtle population is by it telling us the population is increasing by 20% every year. The way we calculate the percent of something is through multiplication. So I would have to take the previous year's population and multiply by the appropriate amount. So our model is going to be exponential since I'm multiplying the previous year by something to get the next year. In order to figure out our model, let's try to figure out the population of our turtles at 2 different years. We know at the start, which would be t equals 0, our population is 100 turtles. What would be our population next year at, say, t equals 1? Now, how many turtles are we adding to the population? Well, we're told that our population is increasing by 20% every year. Since time is passing by 1 year and our turtle population is increasing by 20% per year, the number of new turtles we're adding to the population is 100 times 0.2. But this would only represent the number of turtles we're adding to the population. We also have to include the turtles that were originally there, which means after our first year, our population would be 120 turtles. Since we know our model is exponential, we know that our population as a function of time should equal a times b to the t. Now we can figure out a and b. Using the fact that when t equals 0, p equals 100, we get that 100 equals a times b to the 0. Since b to the 0 is 1, anything times 1 is itself, this will tell us that a equals 100. Now we're going to use the fact that when t equals 1, p equals 120. b to the first would just be b, and we already know that a is 100. So 120 equals a times b to the first becomes 120 equals 100 times b. Divide both sides by 100, and we get that b equals 1.2. So what would be our function that models the population of turtles? d of t equals 100 times 1.2 raised to the t. This is indeed an exponential growth since our base 1.2 is greater than 1. For the next part, how many turtles will there be after 5 years? 5 years is a time, so we'll set t equal to 5, which means we're trying to evaluate p of 5. So p of 5 would equal 100 times 1.2 to the 5th. Exponential functions can be rather difficult to evaluate by hand, so we'll turn to a calculator. Here I'll use the scientific calculator from Desmos, and we'll just type in 100 times. Now you don't need a parenthesis with the times, so we'll put 1.2. And to get the exponent, we're going to hit this a to the b button, and then to the 5th. If you're using a graphing calculator, in order to use exponents, you want to look for a key that has that upwards looking arrow that we usually refer to as a caret. That will tell your calculator that the number that comes after it is supposed to be an exponent. But after typing it into our calculator, and we're going to round to the nearest turtle, after 5 years, we'll have approximately 249 turtles. Suppose you bought a new car for $40,000. The car loses 5.2% of its value every year after purchase. we're going to write an equation that represents the car's value t years after purchase. Now, just like in the previous problem, because we're told that the car loses 5.2% of its value every year, the way we would calculate how much value the car loses is by multiplying the car's old value by 5.2%. So since we have multiplication in play to figure out the change, we're looking at an exponential model. Now let's figure out 2 points that would be on our model. We know at the start, which would be when t equals 0, the car's value, which we'll call v, is 40,000. Let's think about what the car's value would be in 1 year after purchase. Well, we know our car is losing 5.2%. So whatever our old price was, which is 40,000, it's going to lose 5.2% of that. So minus 40,000 times 5.2%, which is 0.052. If we go into our calculator here in Desmos, punch that in, we get that the car's value after 1 year is $37,920. Now let's figure out our model. Our model, because we're working with an exponential growth or decay, is going to be in the form of v of t equals a times b to the t. Using our first piece of information, plugging in 0 for t and v for 40,000, since b to the 0 is 1, a times 1 is a, we get that a equals 40,000. Using our next piece of information, if we plug in 1 for t, we should get that v is 37,920. But b to the first is just b, and a we already know is 40,000. So to solve for b, we'll divide by 40,000. So we have b equals 0.948. So now that we know a and b, the v of t is going to equal 40,000 times 0.948 raised to the t power. Next, how much will our car be worth after 5 years? This means we're trying to evaluate v of 5, which means we're going to plug 5 into our equation for t. And we'll go into our calculator, type in the 40,000 times 0.948 to the 5th power. Since we're dealing with money, we'll round to 2 decimal places, and our car after 5 years will be worth $30,626.80. A classic example of exponential growth is compounding interest. Compound interest is where new interest is earned upon previous interest. The first form of compounding interest we're going to look at is interest that compounds n times per year. In this model, our variables are going to be the following. First, P is going to represent the principal. This is our starting amount. R is the annual percentage rate, which we abbreviate as APR. Be careful when working with R. R is presented as a percentage. Remember to convert it to a decimal for calculations. T is going to be the amount of time in years that we leave the money in the account. And A is the amount of money after T amount of time has passed. Now, A doesn't just include the principal that we invested, but it also includes the interest we've accumulated over that period of time. How do we calculate the compound interest that bears interest compounding n times per year? We're going to use the formula A equals P times 1 plus R over n, all raised to the n times t. Suppose I invest $20,000 into a savings account with a 4.5% APR for 10 years. We're going to go through and calculate how much money will be in our account based off of a few different scenarios. Those scenarios are going to be the interest compounding annually, the interest compounding quarterly, or the interest compounding monthly. Now, I already have the compound interest formula written at the top. Let's take a moment to identify P, R, and T, as that is going to be used in each part. Our principal, our starting amount, is 20,000. Our APR is 4.5%, which is 0.045. T, our time, will be 10 years. Now, in each part, we do have to identify the value of n. Recall n represents how many times per year our interest compounds. So taking a look at the first problem, we're told our interest is compounding annually. Well, if something happens annually, how many times per year does it happen? It would happen 1 time per year. So A, the amount in our account, will equal 20,000 times 1 plus 0.045 over 1 raised to the 1 times 10. Going into Desmos, we will punch this into our calculator, and we get that A is $31,059.39 when we round to the nearest cent. Next, we'll figure out how much is in our account as we compound quarterly. If something happens quarterly, how many times per year does that happen? Well, that would be 4 times per year. So when our interest compounds quarterly, n will equal 4. So A will equal 20,000 times 1 plus 0.045 over 4, all raised to the 4 times 10. Going into Desmos, we'll just replace the 1 from the previous problem, the 4, and we get $31,287.54 when we round to the nearest cent. Notice that our amount when we compound quarterly is more than $200 more than what we would have if we compound annually. The reason why we're getting more here for quarterly is because our interest is being calculated every quarter. We have more opportunities for that interest to accrue more interest. Next, how much money will be in our account if the interest compounds monthly? Well, if something is happening monthly, how many times per year is that happening? That would be 12 because there's 12 months in a year. So here, n will equal 12, and you get that the amount of money in our account is 20,000 times 1 plus 0.045 over 12 raised to 12 times 10. Going into Desmos, we'll replace the 4 from the previous problem with 12, and we get $31,339.86. Notice again, this amount is more than what we would get if we compound quarterly. This is because, again, there are more opportunities for the interest to accrue more interest when we compound monthly as opposed to quarterly or annually. A value that will oftentimes appear as a base of an exponential function is the number e. The number e is defined to be the number that 1 plus 1 over n raised to the nth power approaches as n increases without bounds. Another way to say this is as we make n larger and larger, the value of 1 plus 1 over n all raised to the n is going to get closer and closer to this value e. E is approximately 2.718288182, and the ellipses are to indicate that the digits go on forever. Furthermore, there's no pattern to the digits after the decimal place, and this is because e is an irrational number. Because e pops up so much as a base in exponential functions, e is often referred to as the natural base. The mathematician Euler did a lot of work studying e and its application, and for that reason, e is sometimes referred to as Euler's number. The number e is often used as the base of an exponential function that represents continuous growth or decay. If f of t equals a times e to the rt, then f of t represents continuous growth if a is greater than 0 and r is greater than 0. On the other hand, if a is positive while r is negative, then our function represents a continuous decay. What we mean by continuous growth and continuous decay is that our substance that we're studying at every instantaneous moment is either growing or decaying. An example of continuous growth would be, say, modeling the population of bacteria that can grow very quickly. An example of continuous decay would be something like radioactive decay, where the amount of the substance is decreasing every single moment. The absolute value of r is referred to as the relative rate of growth or decay. Keep in mind, the reason for the absolute values is because r itself can be positive or negative. If r is negative, then we call it a decay rate, whereas if r is positive, we call it a growth. A classic example of continuous growth is when interest compounds continuously. The difference between interest compounding continuously as opposed to monthly, annually, or quarterly is that every instantaneous moment, interest is being calculated. And that interest is also accruing more interest for the next instantaneous moment. So it's not just after a certain period of time we're recalculating the amount in the account. A, P, and R all still have the same meanings as they did when interest was compounding n times per year. Now we'll return to the scenario where I invested $20,000 into a savings account with a 4.5% APR for 10 years. This time, we're going to determine how much money will be in the account if the interest compounds continuously. Now, we've just discussed a second formula for how to calculate compounding interest. How can I tell which formula I should use? The key is to identify how our interest is compounding. If our interest was compounding n times per year, whether it be monthly, quarterly, weekly, daily, annually, that tells us we're using the first formula, the p times 1 plus r over n all raised to the nt. The only time we don't use that first formula is if it compounds continuously. If our interest compounds continuously, then we're using the a equals pe to the rt formula. To use the formula, we have to identify p, r, and t. Well, those are going to be the same as what they were in the previous problem. P is going to be 20,000, r will be 0.045, and t will be 10. So the amount of money in our account after 10 years will be a equals 20,000 e raised to the 0.045 times 10. Going into Desmos to evaluate, anytime our base is e, we will want to use our calculator or Desmos to evaluate. So we have 20,000 times. To use the number e, we just have to type in the letter e and then raise to the 0.045 times 10. And we have $31,366.24. Notice that above the $31,339.86 was the amount of money in our account if our interest compounded monthly. That is less than the amount of money in our account when it compounds continuously. Assuming we keep the principal, the rate, and the amount of time the same, interest compounding continuously will yield more interest than that of when our interest is compounding n times per year. This is because we're calculating the interest every instantaneous moment. So there's infinitely more opportunities for the previous interest to accrue more interest.